Yeah. Right. So yeah, I agreed to talk about KiCad because I've been using it for a couple of years now. I mean, I've been doing sort of odds and sods of electronics for decades, basically, and I've always been hand wiring them. I'd never really thought there was any point in making my own PCBs. I did experiment with us quite a few years ago. But when I started to come across doing the Micromouse, I suddenly realised things were starting to get quite small and quite difficult to do, especially when you go into half size. With half size, I was finding it incredibly difficult to sort of trying to squeeze everything into the space. So that really what kicked off my interest in going PCBs, using my own designs. And one thing I thought it was going to be a problem is that A, it was going to be difficult to do the design, and B, it was going to be expensive to get the PCB made. But then I discovered various other people were saying, no, actually, it's really quite easy to do design, easy to do the manufacture, very cheap to use Chinese manufacturers and so on. So I thought, well, we'll give it a go. And I was recommended KiCad as a good tool to go for, and that's what I've been using. And to be honest, I wouldn't go anywhere else now because I'm familiar with it and I'm really happy with what it's been allowing me to do. So what is KiCad? Well, KiCad is a fully featured design tool, so it allows you to design the circuit diagrams, lay out your PCBs, and generate all the data you need to send to a PCB manufacturer to get PCBs made to your own specifications. So you no need now to go to expensive, I remember using AutoCAD and things many years ago. They were very expensive tools. But this is completely free and seems to be very capable, and I haven't had any problem with it at all. The things it includes is a rules checker at each stage of the design. So though it's not doing a full simulation of your circuit to make sure your circuit diagram is consistent and accurate and obeys all the technical specifications of the components, what it does do, it just makes sure you do the basics right. So you have wired everything you think you've wired together, that inputs to your Arduino Nano or whatever you're using are wired to things that should be wired to inputs and not things that should be wired to outputs and things of that nature. So it's done a lot of that. And similarly on the circuit design itself, when you're doing the layout of the PCB, it's again making sure there's a lot of rules obeyed in there to make sure you're not making any silly mistakes. So it's not foolproof, but it does. But in my experience, it has really cut away all those obvious and silly errors that I potentially would make. I'll come back to that in a minute. The other thing about it is it's free, open source, so no payment required. It includes a whole raft of symbols and footprints, allow you to add almost all the common components you want to add. So all resistors, capacitors, LEDs, phototransistors, Arduino Nanos, and a lot of other stuff besides. There's all, individual ICs are all there as part of the standard design. And you can add your own, and a lot of manufacturers actually provided the files that you can plug into KiCad to actually add those in there as well. So one of the ones I've used is the Seed Studios produce a little board, the Seed Wino, which is a tiny little board you get with various processors on, and they produce the files you put into KiCad to allow you to add those to your designs as well. So that's really good. So once you've used those and got your circuits together, you've got full export capability to get to the manufacturer, and that seems to work flawlessly. I didn't have any problem with that. Once I followed the manufacturer's instructions on what data they needed, it came out, and didn't have any problem with it at all. The other thing is it's fairly agnostic to what it runs on. You can run on Windows, Linux, Mac OS. I'm running here on Windows, and again, I have no problems with it. I'm not going to crash or any real peculiarity in its behaviour. So I'm quite impressed with it generally. So what I thought I'd do today, rather than just me rambling on incessantly about it, I'll give you a practical example. So what I'm going to try and do, now it's a bit of a challenge in the time available, what I'm going to try and do is produce a partial Micromouse design from scratch using an Arduino Nano, 3 phototransistors as the sensors, 3 high-power LEDs to illuminate the walls. So in a similar vein to we've got in the UKMARS standard wall follower sensor board and what's on the main board. I haven't bothered with the motors and things. It was just took too long to do the whole thing. But hopefully I can give you a good feeling for how you can design this. Right. So when you start up KiCad, the first thing you do, you can create a new project. So I've called this demo project 2. And this is the sort of home page you're confronted with. One thing I should probably say is I'm running here KiCad version 6.0, which when I installed this about 6 months ago, it was brand new. Now it's just been superseded with KiCad 7. So I'm not sure what the differences are, but it might be a slight difference if you download the 7 now. But what you've got here on the right, well, on the left here, you've got a tree, which is your project. And on the right, you've got the different editors that you can run and tools you can run to do the design work. So the 2 most useful ones to get you going is the schematic editor, the top one. The third one, the PCB editor. In fact, those are really everything else you can do from within those 2 editors. So if we go first, the first thing you need to do is design the circuit. So you use the schematic editor to enter the circuit in KiCad. So it gives you basically an engineering drawing style sheet. And on there, you start, the first thing you have to do is start adding the components that you're interested in designing the circuit with. It calls them symbols in the nomenclature of the tool. And there's this little add a symbol icon up here, and you can do the same up the menus. But if you press that, what you'll get is you should get you should get a window up. Where's that gone? Oh, that's very odd. Normally that comes up instantaneously. I'm not sure why it was so slow. So what it comes up with is a browser for all the different components that you might want to add. So you've got, the old CMOS series, 4000 series. You've got the TTL, 74 series, and a whole bunch of other things within here. So if I want to add my Arduino, you've got a search here, so you can just type there. So it hasn't got every single one, but it's got the common ones, Arduino Nano and Nuno and various other things in here. So I'm going to pick the Arduino Nano version 3. So we just click that and add it on. When you add that in, what it's done, it's defined all the pins that the Arduino Nano has, and it's given them all names. And behind the scenes, what it's also done is define rules on what they are. So, for example, the power pins are defined as power pins. Those, the 3.3 volt and the 5 volt are outputs. The VIN is an input voltage. Reset is inputs. The analogs are inputs. Most of these are input and output. So what it will eventually do is use those rules to govern whether you've got a sensible circuit or not and when you wire it up correctly. So I've added that in. Next thing I want to do is add a couple more things. Hopefully it won't take so long this time bringing that up. Right. So this time I want to add a resistor, say. So a resistor has just got R in here. We can add a resistor. So what I'm going to do is generate the circuitry for the three LEDs to start with. And the 3 LEDs, because we want to drive them at high power, I'm going to use the same approach as used on the UKMARS bot, in that I'm going to have a resistor. And the resistor, I'm going to put up to 5 volts. And I can do that because it has a special symbol here. The earth symbol here is actually any of the power symbols. So what I'm going to do on here is power, and I'm going to say, well, because I want to use an Arduino Nano, but maybe not the original Arduino Nano, but I want to use one of the new derivatives, such as the Arduino Nano RP2040 Connect. Or one of the other derivatives, they generally operate at 3.3 volts. So I'm going to go and add a 3.3 volts, and I'm going to say, I'll add that to that. And I literally just build the circuit like this. So I can do that, and I'll quickly just add a few more components. So I'll add capacitor. So capacitor is just a C on here. All right. Oops, no, I didn't actually want to add that capacitor. I wouldn't do that. There's two types of capacitor you can add on here. You can either add a C, which is just an unpolarized capacitor, or you can add, a polarized capacitor, which is one that's the bigger electrolytic capacitors typically, which have to be wired the right way around to the power. So again, I'm going to add a power. This time I'm going to add my 0 volts, which is ground. Right, I'm just going to add that on there. So I've got this is going to become my power supply for the power in the LEDs. And we're going to put a resistor in here. And that resistor, we need to give it a value. So at the moment it's got R question mark, doesn't know what it is. Double click on it. Right, and you get a dialog which basically allows you to enter a number of bits of data about it. So since I'm running this at 3.3 volts, I'm actually going to use a resistor. I'm going to use a 3.3 or 3R3, so I'm going to enter it, 3.3 ohm resistor for that value there. So I've done that there. Similarly on the capacitor, double click it. Right, the value on there I want to be, let's say 330 microfarad, is a reasonable capacitor. Right, so I've got my basic circuit for getting some power to the LEDs. Now I want to add the LEDs themselves. So again, I want to add another resistor. Let me get this right. Yeah, another resistor. I want to add an LED. So again, there's a number of types of LEDs, but the sort of we use here is just a generic LED. All right, that's come up, but it's come up as a different orientation of one. So you can just hit an R and it'll rotate it round. Again, we can just link it on. And we want a bit of a circuitry to switch that. So to do that, I'm going to add a transistor. So I'm going to use the same one on the UKMARS box. That's a BC337 transistor, NPN transistor again. And really I'm just building it up like this. Again, resist, that needs power. So that's going to go to ground. Oops, didn't mean that. What did I hit? Ground, thank you, ground. Right. So that's my basic circuit. This is all being powered from that capacitor. Let me just smarten up a little bit so I can bring it down so it's all leveled up. And now what I want to do is I want to basically I'm going to do 3 LEDs. So let's have, let me just move that out of the way a bit. So I'll just move it around. And what I want to do is basically, put some values again on here. So the LED, I just realized I made a mistake on that already. Oops. Try that one again. Right. I had the wrong value on there, so I'll just fix it to, it should have been a 10 ohm, that one. That one's the 3.3. The LED, it's just come up as a generic LED. So I'm going to say, well, actually, no, I want it to be more specific than that. So I'm going to use the high power red LED. It's the TLCR 5800. Because we can pulse that one up to about an amp. So that's why we've got this capacitor as a reservoir to pump the circuitry in there. And we got another couple of resistors to do that as well. So if I want to duplicate this, so at the moment I'm going to put 3 of these. So I can just cut and paste these. So they're all going to be the same. So I can just link them all up. I might want to move them around a bit just to give them a bit more space, but I'll leave it for the moment. So that's our basic circuit diagram. Let me just complete what we've got. We've got another couple of resistors. I can just start bringing these together. So you can see that basically I can build up the circuit quite quickly with this. Right, so that's ground. Right, so we have our basic, so we've got 3 LEDs, 3 limited current resistors of 3.3 ohm. We've got a capacitor to store the charge, so we don't overrun the burn out the LEDs if we try and drive them. And what we then need to do, actually, yeah, if you click on the resistor value instead of the device itself, it just comes up with a single value. It's the same. It's basically the same diagram. So I'm going to put a 220 ohm resistor in there, and I'm going to put for this one here. I'm going to put in a I don't know, 10K, something like that. Right. So the next thing I need to do is start wiring this up to the Arduino. So what we can do to say, well, that one there on the UKMARS bus coming from D12. So what I can do is basically just literally, oops, make a complete mess of it. Yeah, you can come around and just wire it up to D12 if you wish. Oops. And that's perfectly well a valid way of doing it. But as soon as you get a lot more components on it, you finish it with getting wires everywhere. And what you'll find is when you eventually come to the PCB design, it doesn't really know what to call that wire. What they term a net in this jargon here. So what is often a good idea, particularly with things like the MCUs like the Arduino Nano, is rather than wiring it up like that, is what we can actually do is put a label on. So I'm going to put a label on and call it D12. All right. So that D12, I'll rotate it around. I'm going to attach D12 to that resistor. I'm going to copy it and I'm going to attach D12 to that pin there. So what that means is that all the D12s are actually wired together. And what you then find is it can simplify. You can break down the circuit into little pieces without having to have wires everywhere and make it very difficult to read. That is particularly useful when you've got a lot of signals. For example, I don't really got enough time now to add the phototransistors on here because I literally haven't got the time to do it. But give me 10 more minutes, I would have been able to do that. And then when you've got 3 in a row, then it becomes a bit more obvious on how to, what you need to do to get that, simplified on that way. So if we look at what we've got here, once you think you've got up to a point of having a valid circuitry, a circuit diagram, what you can then do is run what they term the electrical rules check. So if I run the electrical rules check, it comes with the dialog and hit run. And what it'll do, it'll go through and basically look at all the rules that it thinks you've violated. So all these simple errors that I made, it will be highlighted. And you really need to do this continuously. So you change the diagram, you go and do the checks, fix up a load of issues, and keep running that until you get to the point you've got 0 errors, 0 warnings. At the moment, I've got 43 errors, no warnings, interesting enough. But some of these are a common problem. What you notice there, the first thing's highlighted, is put a little red arrow on everywhere that's got the got an error on here. What is highlighted is that I've got an R question mark on each of my devices and a D question mark. Now they are the internal references of those devices. And when you go, if you ever got to get somebody to make this professionally, including putting the components on, you need a unique reference for those components. So you can go in. I mean, for example, if I wanted to, I can go in here and basically manually add a reference for that. So I could call it R1 or R99 or resistor 1 or whatever reference I want to call it. But the easiest way to do it is basically allow it to use its default prefix, which in this case is an R, and then automatically generate all the references. So I can do that. If I go up to here, there is that one where it says R question mark to R42 icon. If I hit that, and then annotate, what it'll do, it'll create numbers for everything that hasn't got a number. So it's called this A1, the Arduino is A1, it's called this R1, R3, R5, R6, and so on. So if we then run the consistency check again, we're a lot better. But what you'll find is the first thing you'll usually hit is something like this: input power pin not driven by any output power pins, and pin not connected. Pin not connected basically means that D0, D1, etc. are not being used on Arduino Nano. So it's not liking the fact I haven't connected anything. So there's a special on the toolbar here. There's a no connect flag, or Q for short. So I can click on that and I can literally go say, well, actually, I'm not using any of these at the moment. Right. There's quite a few of these at the moment. But I mean, I'm deliberately not using these. Right. All right, let's try that. So I can then run the check again. And you can basically just keep going around this loop until you reduce the number. So I'm down to 11 errors now. Right, input power pin. Oh, I forgot to add my power, didn't I? So I need to add a power connector. So my power connector that I'm going to use is a, let me just check. It's a, yeah. If I go down to the connectors, there's a whole series of connectors that are defined in here. The one I'm going to use is just a generic 2-pin male, 1x2-pin male generic connector. It'd be very exciting. And what I'm going to do is then say, well, maybe pin 2 is maybe my VIN, my battery voltage. Oops, sorry, I need to click that. And pin 1 is my ground. Yeah. Right, so I now run my consistency check again. Right, and interestingly enough, I'm still getting the error there, but I'm getting a different error now. It says input power pin not driven by any output power pins. What that means is, although I've got pin 1 and pin 2 I'm going to use as my battery, this KiCad doesn't actually know that they're my battery pins. So what I've got here is that, yeah, you've connected the two together, but it doesn't really know what that means. Now, to get around that problem, you have to tell it that that is a power pin specifically. So I can do that again on, if you go to that ground icon, there's some special power flags in here called PWR_flag. And what you do, you put that on there, and then I'll do the same on the ground. Right. What that's doing, that's telling KiCad that that's a power input for the 5 volt, the battery input, and that's the power input for the ground. So if I run the check again, and you get the idea. You're getting, yeah, we're getting to the point at which we're reducing them. We're now down to 9 errors. I'll just finish off a couple of things on here. What I didn't do is say my 3 volts, the 3.3 volts on the circuitry is actually coming from the Arduino Nano. I'm not interested in the 5 volts. I'm not going to use that. Let's run it again, and so on. So you can just cycle around this. I haven't really got enough time to go through the full lot, but it's in essence, it's you know, you just, yeah, again, I noticed there wasn't, I forgot to annotate the new diagram, the new component. So, oops, didn't mean that. Sorry, didn't mean that. Right. Okay, what did I miss? Yeah, what I've got is a row component there. That's another one it had noticed, so I'll delete that. Right. Yeah. Anyway, so A1 didn't like A1. Didn't like A1. Pin 29, pin 4. Oh, right, no, sorry, I realised this down here. So again, ground. I've forgotten to attach these two to ground. Right, so both. I'm just about there, aren't I? Just about there. Yeah, there we go. So I'm down to 0 error, 0 warning. So I've got my basic. What I can then do, if I quickly, oops. Yeah. Sorry, I've just lost the window. All right, so that's as far as I'm going to go for the circuit on there. So once you've got the circuit design clean, and hopefully your design you know is electrically valid, because it's not doing any electrical tests, but it's at least it's connected up as you specified it. What you then need to do is go to the next stage, and the next stage is basically identify what physical components you're going to use to put this on the PCB. So are you going to use through-hole technology to do classic the hole through the PCB and manually solder it, or are you going to use a slightly more modern surface mount technology and basically just use a reflow oven or a hot plate or whatever to mount these on the surface of the PCB. The advantage of the surface mount is that you can get them in a lot smaller packages. The advantage of the through hole is it's very easy to do manual soldering and very easy to change if you want to rip a component off and add another one on if there's a faulty or you've got a wrong value or whatever it might be. So it's at this point here you've got to then start to decide what you're going to actually do. Now, for the purpose of this example, I'm just going to say we're going to do through-hole plate for everything. So next thing I need to do is run the footprint assignment tool. So if I run the footprint assignment tool, what it has actually done on here, it's already pre-populated to, because it knows the Arduino Nano and what the footprint of that is, so it's automatically populated that. It's already populated my transistor, but what it hasn't done is populated anything else. So what we need to do is go through each of these in turn. For some reason that's not working. Why is that not working? Oh, that's better. So C1 is my 330 microfarad capacitor, so I need to decide what capacitor I'm going to use. I'm going to use a through-hole plated capacitor, so capacitor THT is a through-hole capacitor, and then it gives you a list of all the available shapes and sizes of the capacitors of that potentially can be. So what I'm actually going to do is pick the 6.3 millimeters by 2.5 millimeters, which happens to be the one I've got in my stock. Similarly for that LED, I'm going to decide what the LED one is going to be. So if I go down to LED, again, through-hole plated LEDs, and there's a whole raft of different shapes and sizes of LEDs. So I'm going to go for a horizontal mount, a 5 millimeter horizontally mounted 3.81 by 3.0 millimeter. Right, so if I just do the same for all those. And the resistors I'm going to use, again, if you go down to resistors, you'll find resistor through-hole plated. There's a whole raft of these in different shapes and sizes. So I'm going to go for the ones that I've measured, that I've got in my drawer, and it's 6.3 millimeters by, let me just check the right one. Yeah, so it's that one, 6.3 millimeters by 2.5 millimeters by 7.62 millimeters horizontal, and they're the ones I'm going to use. So I'm just do them all the same. Right, and then the connector, final one I missed. What you really want for power a polarized capacitor, polarized connector, I should say. So the one I'm going to pick for this is a Monex connector, and that is called a, if I can find it. Right, so Monex connector, and I'm going to use the KK254, which is that one there, I think. 1x2 vertical, yeah, that's that one there. Right, so now I've got all my physical components associated with the symbols I've added. Now I'm in a position I can start to add that to a PCB and create a PCB design. Right, so back to my circuit. Next thing I want to do is go to the PCB designer, and that's a little convenient icon here on the toolbar. So I can go to that. Of course, it comes up on the wrong window. Try that window. Right. So the PCB designer is a similar editor. It's slightly more, there's a few quirks to it, but it's basically an okay editor. The only thing that I find a bit annoying with it is that the drawing tools are not very smart. You can't put constraints and sizes and various things on them very easily. So it's a bit limited what it can do, but it does the job and quite usable. On the right here, you've got a list of what they call the layers. So the layers can be things like copper layers, where all the circuitry goes. So you've got a front copper layer and a back copper layer for a simple, the default two-sided board. Everything I've done, two-sided is perfectly adequate. If you go to multiple layers, you can do it, but I don't see the point for the sort of level of work we're doing here. The other ones that are really interesting, you've got the silk screen, which is basically the printing on the board. So you've got the front printing and the back printing, silk screen. You've got the mask. So the mask is where it puts a coating over the copper to stop solder accidentally going onto there. So generally speaking, when you get a board and it's sort of a green PCB, the green is actually the green solder mask that's been painted all over everywhere, apart from where you want this copper to be exposed, so you can connect to it. And the other really important one is the edge cuts. The edge cuts govern how it's going to be cut to make it the size you want. So I'm going to start with that because I think it's easier to start with the layout of the board, physical layout of the board, before you get to try and put anything on. So if I'm going to go, so literally I can edge cut, a line. So I'm going to make a very simple board here. I'm going to go 85 millimeters roughly by, I don't know, 70 millimeters, bit of diagonal, I don't know, whatever, something like that. Right. So that's my basic design. I haven't been very accurate in my measurements, and I'd probably want to go and adjust it. But one thing I would suggest is I quite like using the raw line tools and the arc tools instead of using the squares and the polygons, purely because, particularly on the square tool, if you added a square, all you've got is, well, rectangle tool, I should say, all you've got is a rectangle and you can't change it. I mean, if you want to suddenly put a slope on one end or a rounded edge or anything like that, you can't do it. You've got to delete it and then re-add it. So it's easier to add it from scratch. So I'm just, oops. Yeah, so I'm just going to make this look a little bit closer to symmetrical. Yeah, and what you notice is when I'm changing it here, it's not all these joins, although it's marked them as join, they don't stick together like you might do in a typical graphics package or a 3D designer tool. But anyway, so that's going to be my basic design. If you want to put any holes on here, you can put a circle on, for example, to put a hole. So I can put a couple of holes. Although I must admit, I'd probably not recommend you use the hole tool to put holes on, but you can if you wish. The reason I would say that is because if you then put any copper or anything else, any tracks near that hole, it won't have any rules to say don't go very near the hole. And so you might find you'll be putting lines far too close to a screw or whatever you're going to put into those holes. The better approach is to actually add a footprint. So in the same way as I assign footprints to the individual symbols we added in the circuit diagram, I can also add a footprint, and part of the footprint you've also got a whole series of holes in here. So if I want to put an M2, well, let's go slightly bigger. Let's say I've got I want to put an M2.5 mounting hole. I can actually automatically get it to add a 2.7mm hole, which is big enough for an M2.5 screw, and I can just add that. And what you'll tend to find is it puts the hole in, and then it puts a surround around the hole, which basically says nothing should be routed anywhere nearer to that. So anyway, so that's a little lesson I found. The other thing you'll notice is that when you've added that, it's added a lot of annotation. All this ref and mounting hole is stuff that's going to go on the printing. And generally speaking, for holes, you don't really want printing on the round holes. So what you can do is if you double click on this, sorry, I didn't mean that. Double click on it correctly. You can actually say, yeah, I don't want that, don't want that, don't want that. I don't want to show anything, and I can perhaps give it a reference. Well, actually, I don't care. It's a non-applicable reference. Don't really need a reference to a hole. And then you see you've got a hole in there. So that's my basic outline of my mouse. So now if I look at use the view 3D, I can immediately get a 3D render. Oops. Of that PCB. Not very exciting at the moment, but it just verifies that I've got the shape and I've got the hole. And oops, come back. Thank you. Right. So that's good. So the next thing I need to do is then start adding some stuff to the board. So to add the stuff to the board, there's a little icon here, update PCB with changes made to schematic. So what that means is anything I've defined in my schematic is now going to be dragged into the PCB. So if I hit that, it says what it's going to add, do an update. And what it does, it basically throws them straight onto the schematic. So the next time you then need to do anything is you then need to start moving these to appropriate places on your board. So there's my power connector, there's my Arduino, and so on. Right, this is my, oops. So I'm not sure which one is, I haven't checked, but anyway. Right, so rotate them around. So just get the semblance of a mouse going. Right, so there's my three. At the moment, I've got three forward facing. If I do a rotate, the only thing it lets me do is do 90 degrees. Now, obviously, I probably want to have intermediate angles. So if I double click on that, I can now put down the bottom here, I can actually put any angle I like. So maybe I'll do it as a 225 degree. That's facing outwards, and I'll do the same one here. And that's, what would that be, 135, according to that. Right, so anyway, so yeah, we get it somewhere. Right. Oops, sorry. I do find it's very easy to double click things in this designer. So I'll just bring everything on the circuit in a suitable place. Which one's that? Right, I'm getting there. Something like that. So once I've got them in rough position, I'm not sure that's necessarily the best positions, but it just gives you a flavour for what you want to do. You then want to then you need to wire these all together. So it puts these white lines in, which is the things that aren't connected, an indication of where they are. And it's just a case, on this version of KiCad, it's just a case of manually adding all those tracks. On the latest one, I believe they've added an extra tool which helps automate some of this, but I haven't got that, so I will have to do these manually. So you can decide which you want, whether the tracks on the front or the back. Well, let's say for the sake of argument, I'll put them on the back. So I can then just click on the line tool, and basically I can wire that to that, and I can wire that to that, and I can wire that to that, and I can wire, and so on. And basically you can go, and go. And the only thing, so that's your basic design, and you would just basically go and just wire all these two together. There's only two things I would suggest on top of that is that you really need to do. One is that what it tends to do by default is put a very thin wire between all the things you connected. Now, a very thin wire is no problems for most signals in a digital circuitry of this nature, but a very thin wire is probably not the best thing to do for the power side of it. So what you can do, you can actually define net classes and what their defaults are. So if I go into, no, not that one. Oops, why is that not coming up? Right, so by clicking that, I can define my net classes. So what I might want to do is add another class. So I'm going to call it a power net class. And I want to say, instead of having a track width of 0.25 millimeters, maybe I'm going to up it to 0.5 millimeter. And if I want to make sure it misses other things by a bigger margin, I can add it, and I can do various other changes. That's all I'm going to do on that. But what you can do then is basically say for this power, anything that's marked as ground or everything that's marked as my 3.3 volts, or if I had other power things like motor connections, a good example, you could flag those as using that track width as well. So that means when I get around to marking the connecting these power lines up, it may not be immediately obvious on the screen here, but it's twice the thickness now. Oops. At least it would be if I clicked it right. Try that one again. Yeah. So they are. Well, at least the power is. I'm not quite sure why that one isn't. But anyway, it should be the same. So what it's done is marked all those power. The only thing I would also suggest is that when you are designing this circuitry, it's very well and good to link up all the tracks manually and the power all manually. But usually the easiest thing, and probably the most advised thing to do, is if you want to, when you want to link the ground plane together, is basically create everything that's not a part of the circuitry, you basically mark as a ground signal. And what that does, that helps make more immunity to any extraneous signals, any RF signals. If you've got Bluetooth or whatever on here, it stops that interfering with the signals as much. And it also means you've got a nice low impedance, low resistance to ground for everything on the circuitry, which means that your phototransistors and whatever are a lot more immune to noise generated by the rest of the circuitry. So to do that, you can generate what they call a fill zone. And this is just you basically just draw a tool. So I'm going to say this is a fill zone on ground. I'm going to do it both sides of the board. Right, so I can now just say, well, anywhere in this region. Right, then bring it back to the beginning. Right, missed there, but never mind. And then in the menu, there is a fill all zones. What it'll do, it'll fill that ground. So where there's tracks, there'll be a gap either side of the tracks, but everywhere else it will have filled it with 0 volts. So if I look at my 3D viewer, I'm now starting to see, the semblance of my mouse there. I've got my 3 LEDs, I've got my resistors, and if you look carefully here, you can see as the tracks and everything else is the ground. So I'm going quite happy with that now. And it's really just a case of ploughing through that. That's probably about as far as I'm going to get actually doing the layout here in front of you. But what you've also got in here, and again, it's a very valuable tool, is what they term the design rules checker. So if you hit the design rules checker, similar way for the schematic, run DLC, what it'll do, it'll run a whole series of checks, and it says how many violations have I got, how many unconnected, how many differences between the schema and the PCB have we got, and hopefully we should get 0, 0, 0. Well, violations I've got 0. Well, I've probably got 0 because I use the inbuilt tool to connect things, and what that does, it automatically puts the gaps between the tracks and make sure it doesn't violate anything. So it's unlikely at this stage I'm going to have anything, but I might have made a mistake or I might have moved something. Unconnected items, where it actually says you should have all these connections and you haven't made the connections, and that's just because I haven't finished this off. So in the same way for the schematic, you just keep repeating like, while there's errors, and you do the same on here. And that's really all there is to it. I mean, give me another half an hour, I could almost have got this circuitry, out of production, from nothing all the way through to actually getting something made for me. So I think that's an extremely fast and easy tool to use. Obviously, the more you get on the circuit, the more complicated it gets to do this layout. And I generally take the approach that you try and get, for example, all the vertical tracks on one side of the board, all the horizontal tracks on another side of the board, as far as you can fit them, and then worry about the odd ones that maybe you can't route very easily. And also, I would very, very quickly say, well, if something starts to become difficult because, for example, you're trying to wire a pin on the Arduino that's one side of the board to something that's way on the other side of the board, you might actually want to just swap it around. You might not really want to use D12, you might want to use D0 or A0 or whatever it might be to have a slightly nearer one. You can go back and tweak that. So that's the main thing. The couple little quirks here that you ought to be aware of, really. One is I added that hole on this board, probably because I want to add a motor at some point and I need a way of mounting the hole, so I probably have a couple of holes both sides of the board to mount the motors on. But by adding things and also by editing things on the PCB layout, you're very easily going to start to become, the PCB is going to become adrift from the schematic you had. And in the case of a hole, well, you've added a hole on the PCB, but you haven't added a hole on the schematic. Well, yeah, I don't really have holes on schematics. Why should I have to? But what you might find is if you update the PCB from the schematic at a later date because you might make a change, it'll say, oh, that hole shouldn't exist here, I'll delete it. So what, generally speaking, you'll do for things like holes, select the hole, and you normally go lock it. And similarly with the border. So it's always a good idea. I forgot to mention this before. Oops, sorry, I missed. If you select, if I can select it. If you, sorry, I'm holding the wrong button now. Where's that not selected? Yeah. So for some reason it's not selecting, I don't know why. Oh, it is doing, sorry. Just a bit faint on the screen. Yeah, so I've selected all the border, and now what I can then do is then lock that. And what that does is if I then accidentally, for example, try and drag it, it'll just say, sorry, it's locked. You can't do that by accident. Similar to the hole, if I say try and drag that, it says, sorry, it's locked. We'll let you override it, but it's usually worth having those locked items on there. Right. The only couple of little tips I would suggest on above and beyond what I've just shown you there is, one is, if for whatever reason you can't rotate a line because it's crossing other lines. So, for example, what I can do is say, I want to route that point to that pin there. So what I can do is I can go up there. Oh, sorry. Let me do what I was going to say. Go to the red, which is the front. No, sorry, I was right before. Try that one again. If I want to go from there and I want to cross that, it won't let me cross that because I've already got a wire going across there, and so it's going to try and take me a long way around. Well, if I don't want to do that, what you can do is get to a point and hit V. Oops, that didn't work. Let me try that one again. You hit V, and a V is a via. And what the via does is it changes the track to be from one side of the board to another side of the board. So if I look at that, what it's done, it's put blue, which is the back of the board. It goes through the board to the other side of the copper on the other side, and then goes to the red, which is the front, and tracks it through there. And that's actually just a very easy way of getting a signal from one position to another position if there's something in the way. Like, for example, you've got a lot of, in this case, a horizontal line, and you need to go across it. With through hole, it's generally a lot easier because through hole is on each of the holes is on both sides of the board, so you can usually route it either the front or the back with ease. But when you get surface mount, it's a lot harder because both connections are only on the single side. So that's your basic design. Once you're happy with it, I mean, I've found the 3D viewer really invaluable to give you a quick view, and you think, yeah, that's what it should look like. It hasn't actually put a picture of the Arduino, which is a little annoying, but it has done for all the other components. I quite like that. You can also print. One thing I quite like to do is to print the circuit diagram here. I know you can print that just in black and white, and what that allows me to do is then basically manually place, for example, the resistors I've got to make sure the resistors I've got actually are small enough to fit between the pins that I've defined in my circuit diagram. It just gives me a bit of confidence that I haven't done silly like picked a footprint that's a little too small for actual the physical components. And particularly things like capacitors do come in a variety of sizes. And the LEDs, make sure I've got 0.5 millimeter LEDs instead of 0.3 millimeter LEDs, or things of that nature. So once I've got to that point, and the consistency checkers has said, yeah, everything's okay, what you then can do is, well, you finish basically, you basically need to send it out to a manufacturer. So I've been using JLC PCB. They're based in China. They typically take 3 or 4 days to manufacture a board. They are dirt cheap. I mean, most of the boards I've done, it's normally approximately about, you can get 5 boards for under £5 typically, so less than £1 a board. The only problem you've got is the postage on top of that. So postage is, it depends how quickly you want it. If you don't mind waiting 2-3 weeks, then it might be £20 postage. If you want them like in a couple of days, then you could pay £50, £60 and get them there in a couple of days. But the other thing to be careful, it's nice to know, is that if you're designing more than one board, for example, for my half-size mouse, I've got 2 boards that one fits on top of the other to make it smaller. You can actually send them both off to be manufactured at the same time and pay once the postage. So in effect, it halves it per board cost. So my half-size mouse, I mean, I did both boards and got them back within 2 weeks. I paid for not the premium postage, but the middle level postage. I think it cost me about £30 for the postage. I got 5 of each boards. The total bill was about, I think it was less than £40. So they came within 2 weeks. So I was really happy with that. So to get them to manufacture that I was just about to say, there's an export function on here, and you need to export the fabrication. Sorry, it's not export, it's fabrication outputs. You need to output the Gerbers, which is the files they need. So there's a whole raft of options here, and you basically just need to check with your preferred manufacturer. So GLC PCB says you need to use extended X2 format and various other options here to get the right things. But typically, the defaults are actually fairly good. So you need to generate, this just generates a set of files. You also need to generate the drill files. That's where it's going to put holes in and the edge cuts. And once you've got all those files, you just zip them together, upload them to the GLC PCB website, pay your money, and they start making it. Really, really very easy. So, have I missed anything? A couple of other little things little tweaks on here is grid size. I'm not sure what the right answer to this is, but generally speaking, when you're using through hole, most things are based on a 0.1 inch pitch. So generally speaking, it's quite easy if you stick with 0.1 inch multiples when you're laying things out. So I've got this set to actually a 0.025 of an inch, so it gives me a bit of leeway, but it more or less snaps everything to 0.1 inch. Really makes it quite easy just to lay things out. If you're using surface mount, you might want to use metric, might be easier, or if you're using 2mm pitch connectors and things of that nature, which I've done a couple of times. Sometimes it might be worth just going to a multiple of nice multiple of millimeter, 0.1mm spacing or something. Just allows that to move, to align everything neatly. But it's sometimes quite difficult to mix the units. That's the only thing I would say. Right, I think that's probably all I've got time for on here. Going back to the main menu. So we've covered the schematic editor and the PCB editor. Symbol editor allows you to generate your own custom symbol. So if you find you're trying to use a device that hasn't got anything in KiCad, you can always create your own. It's got the full editor in there. Again, you define the shape of it, what the pin names are. You define what are inputs, what are outputs, what are power, and so on. And then it just becomes part of KiCad like any other component. And you can add a photo of the device if you wish to actually mean the 3D render, then shows a photo of it, which is quite nice. I haven't bothered with that as yet, but I do like the idea. Footprint editor is a similar thing, where if you want to create the footprint, if you've created a custom symbol, you probably want to create a custom footprint and use the footprint editor to do that. Again, whether it's through hole or surface mount or whatever it is. Gerber viewer is just when I've done the export of those Gerber files ready for the PC manufacturer, this has a built-in viewer, so you can actually double check that what you've exported is what you thought you'd exported. So that's quite useful just to see that. Image converters to get the images for the symbols and the footprints. Not sure what calculator is. Oh, it's just a bit of redirector for working out a bit of maths for your circuits. So yeah, I mean that's it really. I'll go back to this. Oops. So just summarize the workflow to get your PCB made. So I started from scratch, design your schematic, you add your symbols, sign values and references, you run the checks, keep running the checks until you've got no warnings and errors, sign your footprints, then you lay out your PCB, right? So I like to define board shape and holes first, export the components, place them, connect them, run the checker until you get no warnings and errors, you export them, and not sure why it says passport.jlcpcb. I think it should just be jlcpcb.com. There's the two URLs that the manufacturers I've used. I've used PCBWay once so far. They were marginally quicker, marginally cheaper, but when I got the boards back, I don't think they were quite as well made in my subjective view. But for what we're doing here, it's probably not a lot in it really. there are UK manufacturers. There are UK manufacturers that do it as well, but they're a lot more expensive. So it's usually easier to go after those for something we're doing, I think. Right. They are just these two here are the two my half-size mouse PCBs. So I did it in two. I've got the sensor board, which is the bottom, which has got your LEDs and your phototransistors and the switching circuitry, and where the motors are mounted. So those screw holes hold the two motors in place. And then I've got a top board, which has got a motor driver chip, and I've got two versions of this one with the motor chip itself directly in, and another one that's got a little module for the motor driver. It's a DR8833 motor driver chip. And that, I mean, for this, I'm using the RP2040 module, which is a Raspberry Pi RP2040 based board rather than the Nano, but mainly because it's a lot smaller. So that's really all I was planning to say. Have got any questions? Anyone wants me to clarify anything?
Neil, one question from me. Design rules. For example, do JLC PCB give you design rule sets? Because sometimes you can just get hold of a set of design rules and load them in. I seem to remember that being there in Eagle. Is there anything similar to that here?
Yes, I think you can. They certainly do run their own checks. Is when you submit them, one of the first things they do is validate that they agree with their design rules. I haven't actually done that. What I was finding is the defaults that KiCad gave me were being accepted by DLC PCB, so I just left it as is.
Right. Okay, thank you.
I mean, I think they get a bit fussy if tracks go just right to the edge of the PCB. I think if you want tracks to go to the edge of the PCB, like a finger connector or something like that in nature, you have to actually specifically ask for it, and else it will bounce it. But,
okay. And the only thing I'd say, there is a hole. Believe it or not, there's a hole symbol, so you can put your holes on the schematic if you want to, which carries them through. I think that I saw as well.
Oh yeah, you probably could. I'm just not quite sure why you'd want the hole on a schematic.
They just don't disappear then.
Yeah. I mean, all I've been doing is just locking them, and then they don't. They just retain there. But yeah, you could well be right. You can create multiple sheets for the schematic, so you could potentially have a hardware sheet which has the holes and other stuff that aren't directly circuitry related, I suppose.
In general, you should put the holes on the schematic. If you want a plated through hole and you want the various properties, it's best to record all that in the schematic, and then it'll populate properly.
Oh, fair point. Yeah. I mean, if it certainly a plated through hole, I probably would have done. It's just the mounting holes. It just seemed a bit pointless, really.
No, thank you for that. Great talk.
Hang on, when you're adding tracks, can you change the width halfway along? So if you've got a power track that's got to go between two pads of your Arduino or something, and you neck it down for a bit and then widen it up again.
Yeah, you can do. If I come back to... so I mean, if I wanted to, I could go. Let's say, for the sake of argument, I've got this one here. I could, start it off one thickness. Oops. Oh no, sorry. Let me try that one again. Yeah, I could start it off one thickness, and then I could come up here and basically go and change. Oh, I haven't added any predefined size. You need to add them as predefined sizes. So if I just do that.
Yeah, that's okay.
Yeah.
As long as it's possible, that's all I really need to know.
Yeah, it's what it generally does by default. So if I, let me add a big one just to make it fairly obvious. Yeah, so I can then go, and then, oops, no, sorry. I'll go there in the end. So I can go and change. Sorry, with the wrong tool. Yeah. Yeah, but I thought you could do it through the drop down. But I think you actually have to type it in if you want to do it. So there we go. So you can have a thick section or whatever it might be. Yeah. Yeah, it can be done.
Okay, thanks very much.
Yeah. On the design rules, I've just been searching my copy of KiCad, but I've upgraded it twice since I last used it in anger and clearly on a different machine. There are templates for JLC PCB and for PCBWay and for many others. Don't ask me where they are, but they exist, and that'll give you the clue you need to go and find them. And you download them, and they set everything up for you in the... I don't even know what window I'm talking to now. They set everything up for you.
Right.
Got your back. And they'll populate all of the various bits and pieces.
Yeah. No, that's good to know, yeah.
Okay. So, anybody else got any questions for Neil?
Do you have something there like this? Basically, we call it like PCB as code, that you like write a YAML file, for example, and then you import it into your schematics in the editor. Have you experienced with things like that?
I haven't done that. I haven't done that myself. Anyone else knows the answer to that?
No, not done it.
Nothing. Okay. But I mean, like, how much could you go in this entire tool there, like, without you using the graphical user interface? Is it possible that you at least like provide the coordinate instead of like dragging it always to the place in the grid where you want to have it? Like when you like click any like element like resistance or like the condensator or things like that, you can.
I mean, you can. Yeah, I mean, you can programmatically position them. Yes, I mean, you can say where you're going to be on there, and if you've got some control, I suppose you could do that. I'm not 100% sure how useful that would be, though, because that means you've got to use some other tool to work out where everything's going to be.
Yeah.
If you want to.
There is a Python interface for the whole thing. If you really want to do it the hard way, you can write code and manipulate the board files.
Yeah.
And so, if you wanted like a circular array of LEDs or something like that, and they are just text files. So again, if you really want, you can open them up in the text editor and mess with them.
There is an example. I just searched for how to import positions of a circular LED array. You might be looking at the same page as me, Pete. I'll paste it in the chat. But yeah, I think there's ways of, as you say, getting being able to do this sort of stuff if you've got a set of components that is, for instance.
Yeah, it might be. You say it might be quite interesting if you want to put input into circles and things like that. I mean, the most I've done is 5 LEDs in a row, and they're so easy to put on by hand that I could put them on by hand. Right, anything else? Do you want to finish off?
No? Anybody else? No? Okay. Neil, thanks very much. We appreciate that, and I think you've added PCB layout tools to the list of animals and children. Well, thank you, mate.
Thank you.